Welcome to the next video. Here we are talking about buffer solutions, which are specific solutions that are designed to resist changes in pH based on the existence of a specific acid-base chemical environment. In other words, if we are to add acid, we have some base in solution that's going to digest that acid. And if we add base, we have some acid that's going to digest that base. And so this is a very important type of solution for regulating pH in our bodies and in the labs. And so understanding how they work is critical to understanding acids and bases more thoroughly. I would say that the concepts of buffers can sometimes be a little confusing, so I would focus on that. The math may come somewhat easily if you follow the Henderson-Hasselbeck equation, but definitely keep in mind what exactly is going on in the solution, and understanding those reactions that are occurring when acid or base should be added will be key to understanding how to understand the more complicated buffer problems. With that, we'll go ahead and jump into the video. All right, so first of all, what is a buffer? We've talked a little bit about the idea that a buffer is going to stabilize pH because it can digest either strong acid or strong base that should be introduced to the solution and therefore not change pH appreciably. But how does it do that? Well, it does so by being a solution that contains a weak acid and its conjugate base that are both present in approximately equal and appreciable amounts, meaning there's enough to digest the amount of acid or base that should show up. And the idea is that if we add a strong acid, it's going to react with the conjugate base. And if we introduce a strong base, it's going to interact with the weak acid. And in doing so, it's going to perform the following pair of reactions. So if the H3O plus is introduced, that's the strong acid, it's going to interact with the weak base, and the following reaction will form, where here A minus and HA are just generic representations for this weak acid and its conjugate base. The same thing here is true for OH minus. If we introduce a strong base, it's going to interact with the weak acid and again become neutralized. So basically, by having both available, it's going to stabilize the pH. If we were to look at how we add acid or base to an unbuffered versus a pH buffered solution, we can see the following, that initially we have the image on the left, which shows both at pH about equal to 8, as the color is pretty similar. There's some sort of a indicator that's present that shows a change in pH. And if we were to introduce something that would change the pH radically, that would occur in the unbuffered solution, but in the pH equals 8 buffer, it won't change appreciably. Now, it is going to change a little bit. If we add acid, it's still going to bring the pH down a little bit. And if we add base, it's still going to bring the pH up a little bit. But it's going to do so in a very small amount, so much that it's really not going to change the pH away from approximately being equal to pH equals 8. Okay, so what we've looked at so far, right, is that if we want to have a buffer, it's made out of a weak acid with its conjugate base. So of these, we may have some potential to make a buffer. So take a look at the following and go ahead and pause the video here and recall what we know about strong acids, strong bases, conjugates, and decide which of the following could make up a buffer. All right, hopefully you had a chance to pause the video and determine which of these could or could not make a buffer. And here are the solutions, right? So A, we have a strong acid and a strong base. So we're not able to make a buffer out of that because if we have a strong acid, then its conjugate base is not going to be a base at all. As we may recall, when we have a strong acid, it dissociates completely, which is to say that its conjugate is not going to want to go in the opposite direction and therefore won't have any basic activity. So without the pair, we really can't have it occur. B and C, they're not conjugate acid-base pairs, and so in order to avoid other unwanted interactions within the buffer, we really need to have them be conjugate acid-base pairs. And finally, D is a conjugate acid-base pair, but it's another strong acid weak base pair, so that's not going to work either, and therefore the answer is that none of these can make a buffer solution. We need to have a weak acid with its conjugate base. The following all would work. We could have H3PO4 and H2PO4 minus, so phosphoric acid and its conjugate would work well, and we could also do that with that deprotonated one more time. HF and F minus is a very common one, as is CH3COOH. That's acetic acid with the acetate ion. That is the acid in vinegar. And all of these acids are weak acids, and what's shown here is their conjugate. Okay, so how exactly does this work though? And here we have a diagram that shows in the middle, that's where we want to sort of view our starting point, is a buffer solution that's equimolar in acid and base. So we have as much acetic acid, CH3COOH, as CH3COO-, so the acid and its conjugate base. If we are to add H3O+, so that's our strong acid addition, it will interact with the basic component and it's going to convert it into that weak acid, right? If we add H3O+ to the conjugate base, it's going to create water and that weak acid. And so all that occurs here is that the acid is going to be digested, the acid we introduced, the H3O+, this is equation 1 that's shown on the left in the center, and we're going to shift the balance from having an equal amount of each to having a bit more acid as it's converting the weak base into the acid. Conversely, if we add strong base, so OH-, it's going to convert the acid into the base and shift the balance that way. Notice that in each of these reactions, shown as 1 and 2, we are consuming that H3O+ or OH- that's added, and what we're doing is we're converting one part of the buffer into the other, and this is why the pH is stabilized. Now, reactions 1 and 2, I think it's very important that you're able to recognize and state these reactions on your own because there are a lot of really similar looking parts in acids, bases, buffers, a lot of similar terminology, and you may feel bogged down by this already, especially as we're talking about adding strong acid as H3O+, but also the weak acid that's present in the buffer and the conjugate base of the weak acid. They all look very similar and they all sound very similar as we talk about it. But if you're able to untangle all of that similar sounding language and state these reactions as we're considering the effect of adding strong acid or strong base to a buffer, then I really think that it'll help solve the types of buffer questions you'll be asked. Again, reaction 1 is showing the addition of acid, strong acid, and how it reacts with the basic component of the buffer. Equation 2 shows the addition of strong base, OH-, and how it reacts with the acidic component of the buffer, in both cases neutralizing this strong acid or strong base addition and just shifting the balance of that buffer. When we talk about buffers, we also want to consider the capacity of a buffer. So while we say that buffers are able to resist changes in pH, this is not something they can do forever. If we have just a tiny cupful of a buffer, it's not going to ever be able to completely digest a gallon of acid that we throw in there. It's just not going to have enough chemical to resist pH completely, which introduces a good question. How much is the buffer capacity? How much strong acid or strong base addition can a given sample of buffer neutralize? And so one thing that's important to know is the concentration of the buffer, because if we have a lot of weak acid and weak base, we're going to have a higher buffer capacity. So in other words, if we're to make a buffer that has 0.5 molar of HF and NaF, note that NaF, sodium fluoride, is how we bring the fluoride ion into solution. So this is basically a 0.5 molar HF and F- solution. That's going to have more capacity than one that has 1/10 of that molarity for each of those species. One of them, the first one, is just going to have 10 times more of both the weak acid and its conjugate base, and therefore will be able to neutralize 10 times as much. We also want to look at the acid-base ratio in the buffer, because if we are looking at a solution, a buffer solution, that has a lot more of one component than the other, then it's not going to be able to handle either acid or base very well, because one of those components is going to be nearly depleted. So in other words, if we have a ratio of the weak base to the weak acid, the conjugate base of that weak acid to that weak acid, that's about 1, meaning equimolar amounts, it's going to have a better capacity than F- to an HF ratio of 1/100. That would indicate that there's 100th the amount of F- as HF, and while this will be able to neutralize base addition pretty well, it's not going to be able to neutralize acid addition very well because there's nearly no fluoride ion in solution, and therefore nothing that's going to be able to pick up H+ if it's added to that solution, and therefore the buffer won't be able to handle acid addition. Okay, so here's a great question that we may want to know, and here what we want to realize is that we have some good equations for dealing with buffers specifically that is called the Henderson-Hasselbalch equation. And we've looked at acid equilibrium, we've looked at equilibrium, and we know that Ka for acids is products over reactants, and when we set up that reaction, we end up getting the following expression for Ka. And this is still Ka. We just, through algebra, take the natural log of both sides, and we end up with this bottom equation that's in red that says that the pH is equal to pKa plus the log of A minus over the HA concentration. In other words, if we have the Ka, and this is the Ka of the buffer that we're looking at, because remember, they're an acid-base conjugate pair. So if we're looking at this solution, we have acetic acid and sodium acetate, which again is really just the acetate ion. The sodium is going to dissociate completely. We're looking at the Ka for acetic acid, because this is what's left behind when the acetic acid dissociates, is the acetate ion. So that's what the Ka is going to be here, and then if we have the concentration of each buffer component, we can calculate the pH. Recall that pKa is calculated in the same way as pH. We just take the negative log of the Ka. So go ahead and pause the video here, see if you can use the Henderson-Hasselbalch equation to solve for the pH of this buffer with the information that's provided, and I'll present my solution in just a second. All right, this one may have been a bit of a stretch, but hopefully you were able to parse out the different parts of this question. Now, the pKa, again, this is the negative log of the Ka. We calculate it just in the same way as we calculate pH from the H3O plus concentration. And in this case, we want to take the negative log of the Ka of CH3COOH, which is 1.8 times 10 to the negative 5, and we end up with 4.74. This is the pKa for acetic acid, just like the Ka for acetic acid is 1.8 times 10 to the negative 5. Just another way of stating the same information mathematically. The HA concentration, this is the concentration of the acid, and that's 1.5 molar. The A minus concentration, this is the concentration of the sodium acetate, which again, the sodium and the acetate are going to dissociate in solution, but we can't just have acetate that we bring all by itself. So whenever we see sodium anything, we really want to just know that this is going to be the anion that matters, which in this case is acetate, which is the other part of our buffer. And the concentration of that is going to be 0.5 molar because it's in a 1-to-1 ratio with the sodium acetate, 1 acetate per sodium acetate compound. This is Henderson-Hasselbalch. We just go ahead and plug in from here, make sure that we evaluate everything correctly, and we end up with a pH of 4.26. This is by taking the log of 0.5 over 1.5 and then adding it to the pKa. Now, one thing that's really great about this equation is let's imagine that the ratio of A minus to HA is equal to 1. And this, as we discussed, occurs when the components of each of the buffer are equivalent. So if we have the same concentration of A minus as HA, then this will be equal to 1. Well, now we have the expression the log of 1. This is to say 10 to the what equals 1. And the answer there is 0. So that part is going to turn into 0. And if that is true, then that log expression just falls out of the equation. And what we're left with is that pH is equal to pKa. And this is going to be true if the base concentration is equal to the acid concentration. And so this is a great way to think about what the pH of a buffer system is centered around. Because what we have here is an acetic acid sodium acetate buffer solution. If they were present in equal amounts, the pH would be equal to the pKa, so 4.74. And this is very important because different chemicals are going to buffer pH at different pHs. They're going to stabilize at different pHs. So if we want to maintain a pH of about 4.74, 4.75, then we can use this acetic acid buffer. But if we want to buffer around pH of 8, for example, then this is not going to be the conjugate acid-base pair that we're going to want to choose. We're going to want to choose one that has a pKa that's closer to 8. Because this condition, where we have the acid and the base equal approximately to one another, that's ideal for the buffer capacity. And so we're going to want to stay around that area. And in practice, we really aren't going to be able to buffer around a pH unless it's within plus or minus 1 of that pKa. Note as well that when we have this buffer, we have more acid than base. We have 3 times as much acetic acid as we do sodium acetate. And therefore, it's more acidic than we would expect, and the pH is a little bit lower than the pKa because there's more acid. having more acid brings the pH down. That's a great way to predict these problems as well. All right, so let's try a question here. Let's say that we have a buffer that's the following two components, and the pKa for this buffer system is given. We want to predict if the pH is greater or less than 7.46, and then we want to actually calculate the pH of the buffer. So again, right, when they're equal, that's when we have this log term falling out, and the pH is equal to pKa. So what are the conditions for this buffer? How is that different than the even composition, and how does that relate to the pKa? Go ahead and pause the video there, calculate the pH as well once you've made that prediction, and I'll show my solution in just a second. All right, so the first thing we want to do here before we get started with the math is to predict if the pH is greater or less than 7.46. And as we look at this, we say, well, it's 0.3 molar of the acid, that's the HOCl, and it's 0.5 molar of the NaOCl, and that's the base, because again, the sodium-containing compound really just has the anion, which in this case is OCl-. So the base is greater than the acid, and therefore we expect the pH to be a little bit greater because base is associated with higher pH. So the value we calculate should have a pH that's slightly greater than the pKa. Go ahead and solve, and we plug in, well, that 0.5 for the A-, 0.3 for the HA, and we see that that's indeed true. The pH is equal to 7.68. The pH is a little bit greater than the pKa. Okay, but what about this, which is a bit more challenging? What is the pH of 500 milliliters of this solution going to be after we are to add some acid to it? So in this case, we want to bring in everything that we've learned in this video so far. And the very first thing is when we add HCl, what is the reaction going to be? Because that's going to determine what our final buffer composition is, right? When we add HCl, this is adding strong acid, and it's going to associate with the basic component of the buffer. So we're going to have a reaction which is the H3O plus from the HCl that's combining with the OCl minus, which is part of the buffer. And what are the products of that, right? How do these buffers even work in the first place? And I would recommend you maybe go back and review what exactly the reaction is that we're looking for, and that was why I emphasized that point so much, is because this is how we calculate the change in pH. Because basically we're going to say, well, if this amount is added, how much reactant is going to be consumed, how much product is going to be formed, and what is the final composition of the buffer after this addition of HCl. If we have the final composition of the buffer, we just use Henderson-Hasselbalch one more time, and we're going to be able to calculate the pH of this system. The other thing you want to keep in mind is that initially this buffer here had a pH of 7.68. If we add acid, how is it going to change? Should it go up or should it go down? So a bit of a complicated problem, but go ahead and pause here and challenge yourself to get through it as much as you can, and we'll review right after that break. All right, hopefully you were able to get a good solid attempt on this problem. If you were able to get the correct answer, I think you should really give yourself a pat on the back. This is a challenging one, and it ties in a lot of concepts that we've learned here about acids and bases, and also ones that we've learned about stoichiometry in General Chemistry 1. So what we want to look at here is a reaction table, and because we actually see that the volume is changing, we want to focus this on moles. So initially, we can look at this buffer and say, well, we have 150 millimoles of HOCl and 250 millimoles of OCl minus, and what we're adding here is 5 millimoles of HCl, which is basically H3O plus. This is the addition of acid here. Set up the following table. This is the reaction that occurs. This is the weak base buffer component combining with strong acid H3O plus, and we see that we're going to digest 5 millimoles of each. This is going to bring our final composition to 245 millimoles of OCl minus and 155 millimoles of HOCl, and that's our final composition of the solution. From there, we just go ahead and use Henderson-Hasselbalch. And one thing that's really great about this is that we don't have to use molarity. We don't have to use any specific unit other than something in terms of moles. We don't want to use grams for Henderson-Hasselbalch. And that's because, by definition, they're existing in the same solution. So even though at the end we're going to have 550 milliliters of solution, we don't actually have to convert back to molarity because both of those 550 milliliters are just going to divide against each other because it's set up as this ratio. If you went ahead and calculated the molarities, that is no problem. You'll find that you still arrive at the same answer. It's just to say that it's not necessary to convert to molarity because mathematically they're just going to cancel out because they're actually existing in the same volume. And the volumes are always going to be the same because they're two parts of the same buffer solution. All right, this is our final answer, 7.66. We predict that the pH will be slightly lower. This is because HCl is being added. And as we've seen, it's really a very small change in pH because of the fact that this is a buffer. To conclude, buffers are a hugely important part of biology. To maintain homeostasis, we need to be able to have a proper balanced pH that doesn't stray out of a certain range. This is essential for our biologies. Mostly we want to have a neutral pH, but some parts like our stomach want to be quite a bit lower. What is really essential though is we don't have any pH spikes that would really be difficult for organisms to thrive under. All right, thank you for watching the video. I hope that this has made buffers a bit clearer, and I look forward to discussing more chemistry in the next one.